Okay, so we continue with Noémie Combe, which is now a work at the University of Warsaw. The title of his talk is Causal Domain on Souriau Thermodynamics.
Thank you very much for inviting. And we don't have this.
Okay, to you.
Okay, so as it's said here, I will talk about Koszul domain and Souriau's thermodynamics. So this morning we had in Frédéric's talk a very nice introduction to Souriau's thermodynamics, and I will rely on this introduction. So the first part of my talk starts with bounded convex domains. So the first example we mentioned this morning was this upper half plane, complex upper half plane or Poincaré disk. So that's a typical example of a bounded convex homogeneous domain. And I will discuss exactly specific examples of this and make relations to information geometry as well as thermodynamics. And at the end, there will be maybe more of a surprise result that I just obtained a few days ago. Yes. Okay. And so maybe this is going to be an exciting topic for discussions. So I'll start with the state of the art. And in particular, what I'm going to discuss today are strictly convex symmetric cones. So it's an example of homogeneous bounded domain. And I would like to highlight how much it interacts in different domains of math. So it's a cone. So yes. So it's just a cone, but it appears in very different branches. So for example, it appears in affine geometry. So affine geometry, and it's already quite, 1935, Cartan already was working on this topic, and it gave the Cartan Hadamard spaces. As well, this was then developed by Koszul, 1959, and there's a bunch of very interesting papers, 59 to 63, a lot of papers about these bounded homogeneous domains. So that's really worth looking in it because Koszul's papers are very nice to read and very clear. So I really advertise Koszul's papers. And now we go to, that was French results in France. And now we go to Winberg, 1963. And remarkably, he's also working on strictly convex homogeneous cones, but from a different point of view. So that's 1963. And from that paper, relations to Jordan algebras were established. So that's one first link from bounded homogeneous domains like these cones to Jordan algebras. So that's already starting to be, well, really interesting because we're, stepping towards an algebraic flavor. So this is what I want to say with this yellow and red box. Then all these cones here appeared to be central or very important, at least, in Hessian geometry. So in 1997, you have the Japanese school this time. So that's really international topic. Japanese school with Shima and developments around Hessian geometry, which appear in those symmetric cones. So that was already a third aspect of the story. And now we have other things that was really incredibly rich, probabilities. So this appears important in information geometry, namely with Chentsov, and there's Chentsov-Morozova, that everybody forgets to mention. So his working partner, Morozova, also collaborated a lot on this categorical aspect of information geometry. So that belongs to the green blocks of probabilities. And in particular, there's a direct application to a type of exponential families, which is called Wishart laws, and which is very popular. So that's the machine learning box. And we're not done yet, because apparently those homogeneous domains, in particular the upper half plane, as well maybe we might know, appears in number theory with modular forms, right? Modular forms are defined on this upper half plane. So Piatetsky, Shapiro, Ziegel, Mass, all these people developed this modular form aspect of the story, which appears for these homogeneous bounded domains. So that was fourth box. And fifth box, well, this is more standard classical, because it's of course related to analysis and harmonic analysis. And maybe this is quite interesting, I think, relations to Monge-Ampère domains and Monge-Ampère operators. And so this is going to be part of my talk today, because it appears in construction that I will be presenting today. So that was state of the art, a presentation of how those cones can be interesting to everyone in very different aspects. So it's really something that we all want here. So I'm going to develop, since we're in a machine learning type of workshop, I'm going to talk about this information geometry side. And so these are just recollections. I'm not speaking about something new right now, but so here you can find works related to Amari. So this is Hessian geometry-like point of view. So I'll start with a bit of probabilities, because maybe we forgot. I doubt it, but we never know. So I'll just recall that a measure is called absolutely continuous with respect to another measure, lambda, if for every measurable set A, we have this implication. If the measure of A by lambda is 0, then P of A is also 0. And so this innocent statement has a nice implication, because it implies the existence of a measurable function rho, so it's the density of the probability if we're in probability theory. And P of A is, of course, integral over A of rho with respect to d lambda. And this for any element A in this sigma algebra that I defined F. So that's it. And so rho, as I said, is the density of the measure P given by the Radon-Nikodym derivative, so dP over d lambda. And so that's pretty much everything we need to know for defining these straightly convex cones in the setting of information geometry. So in particular, you have the manifold. So a manifold of probability distributions of a given type, so a given family. Usually people work on exponential families. And so what is it? Well, so if you have omega f, your measurable space, f is your sigma algebra. And if you consider a family of parametrized probability distributions on omega f, then the manifold you consider is the set of all probability distributions over a finite set. So that's your statistical manifold or manifold of probability distributions. So that's what people study in this information theory aspect of the story. And there's a lot of things to say relating to Hessian geometry. So this morning we had the metric of Fisher-Rao. Typically, it's going to appear here, choosing the right coordinates, of course. And this is where you're going to have the Amari-Chansov rank 3 tensors. Someone was talking about this morning. So this is where it's going to belong to. And yeah, and so that's what we want to discuss. So I just wanted to make another bridge to other things, which is, so this is due to me. And in 2020, we wrote a common paper with Yuri Manin, where it was found that there exists actually a connection between the object that we just discussed before, this manifold of probability distributions of exponential type, and a structure which appears in the so-called mirror symmetry. So Frobenius manifolds. That means manifolds satisfying a given partial differential equation named after Witten, digraph, Verlinde. So in particular, you need some flatness condition. That means when it's no curvature, flat. So when it's flat, it becomes a Frobenius manifold and therefore potentially interesting for mirror symmetry. So that's the more algebraic geometry spectacular kind of input. But I want to say that all these WDVV equations, historically, starting from the point of view of Dubrovin and Novikov, it all has to do strongly with integrable system and bi-Hamiltonian system. It's not a point of view I chose to develop right here, but I want to let you know that it's very possible, that it's just another language. But so bi-Hamiltonian systems are very natural here. So that's the WDVV equation. Phi stands for a potential function, and G stands for a Hessian metric, particularly inverse, GEF. With the EF up is the inverse of the inverse tensor of the metric tensor, GEF down. And the -1, it's not necessarily that you have it. It's just that this equation is extracted from a context of supersymmetry where you have signs appearing. So it's over Z mod 2. But we don't want to talk about this. I just want to say that it exists. So that's one thing, relations to two-dimensional topological field theory from the point of view of mathematics, because I'm not a physicist. So this is from the point of view of mathematics. And so this is a bit more about a mirror symmetry propaganda. So I found a very nice picture by, I think, an American called Mike Feng, who was illustrating his vision on mirror symmetry. And so this is a quintic threefold. So initially, the mirror symmetry started with this quintic, and there was a story about constructing mirror jewels. So you have a mirror with the kind of pale reflection of a quintic. We don't know what that is. And well, it's parametrized by some kind of space. So you see the shadow. So it's actually going to be parametrized by, well, by real manifold. And we will see exactly what this real manifold is. And you have also torus vibrations appearing, so tori somewhere in this kind of crazy looking picture. So that was mirror symmetry propaganda. Okay, so let's be serious now. I would like to express a few statements that I have found. So the archive preprint is coming out tomorrow. So if you want to check it out, you just type my name, Noémie Combe, on archive, and you'll find the exact statements of what I'm going to say. But first, so that was the teaser. And first, so let's take it slowly. And I'm going to speak first of all about the problem of Monge. Okay, so let's go back historically. I think it's always a nice thing to like put things back into their initial context. And so Monge well, he lived at the times of Napoleon, and so Napoleon needed a lot of scientists, well, to study correctly things for his army. And so the very concrete, I think is a very concrete problem, you see those dots here? Well, you can imagine that there are people, and so this is your army, and you have those people scattered, and you want the fastest way, the most efficient way to transport all those people into nice lines and columns. You know, they have to be ordered. And so that's the real problem. What's the most efficient way of transporting a distribution of mass into another? So that's typically the points you see on the right-hand side of my slide. So the question is about finding T. So that's the transport map. And well, miraculously or not, this is given by this Monge-Ampère equation on the left-hand side. So you're taking a Hessian, so the second derivative of a given real function phi, and you're taking the determinant, and you want it to be equal to something, ideally not zero. So you have the case when the right-hand side of the equality is negative and or positive. And I'll focus on the positive side, so it's called an elliptic Monge-Ampère equation. So you can take, for example, constant. Determinant of this d square phi is 3, for example. So that's going to be typically something I'm going to investigate. And so the little thing on the lower part of the slide, infimum of this sum of the distance between each of this point, each soldier here, well, it's going to be a condition of optimization. So it's costing less of energy, of whatever, it costs less. So that's the Monge problem. So I would just want to add that I talked about mass conservation. So it's translated by this type of formula. So that's typically when you have every soldier with mass given, I don't know, x1, x2, x3, you want the mass to be, well, correctly transported. You don't want to lose something, your hat or whatever. And so there is a very fun, well, very nice result by Brignier in 1991 that tells you, well, that given certain conditions, your transport is going to be nabla of phi. So that's a very good statement, especially when you're using it in the context of probability distributions, which is the case in information geometry, or or measures in general. It works also for measures. So this is what I'm going to use to show that this manifold of probability distributions is just, or it is, a Monge-Ampère domain. That means that everywhere locally you have a Monge-Ampère operator. So usually you don't do proofs on talks. That's why I'm advertising my archive paper. So I'm not going to give you the proof, but I'm just explaining the point of view and the concept. So the results are, so I have not yet introduced rigorously my cones. So the cones I was mentioning, strictly convex, homogeneous cones. Well, they're going to form a Monge-Ampère domain. That means everywhere locally, there exists a unique potential function on the domain such that the determinant of Hessian of phi is equal to something which is non-negative. F is a non-negative real function on P. So usually in the Dirichlet problem, you have some conditions on the boundary. For simplicity in the talk, I just omit them. It's all written in the paper. Okay, so that's one thing. Monge-Ampère. The second thing is, well, that I show that the Monge-Ampère domain is something called a pre-Frobenius domain. That means, so as I said previously, Frobenius business is central in mirror symmetry. The mirror symmetry is a duality, an isomorphism between two types of Frobenius manifolds. So here, a preliminary structure, sorry for going so fast, preliminary structure of a Frobenius manifold is a pre-Frobenius manifold. That means I'm not satisfying one axiom, or I could satisfy it, but I have no guarantee. So it's safer to say that it's pre-Frobenius. And so cones that we will define rigorously in 2 minutes are pre-Frobenius manifolds and contain actually a Frobenius manifold. So that's what I want to talk about today. So as I was saying, and I just added a slide just for the sake of clarity, that there exists a Monge-Ampère statement, theorem, for density of measures, but you need to satisfy a condition. And the condition is that the measures have to be almost complex with respect to a Lebesgue measure in order to apply Brignier's theorem. So you're going to transport your density rho tilde into rho tilde prime. And this is going to imply that you're transporting the corresponding measure mu1 to mu2. And via Brignier, you can find that this is in fact given by a Monge-Ampère operator. So that's the magic side of Monge-Ampère theorem, that you can apply it to statistics. So I promised I would be rigorous now, and this is what's going to happen. So I wanted to say, what are those cones? So there's a very nice representation in terms of matrices, which makes us all very happy, because you could give this eventually to a student in second year of bachelor and they would understand what that is, well, theoretically. So one cone, the real cone, for example, is given by square matrices that are positive, definite, symmetric. So it means X transpose A, X is positive where A is the matrix. That's what it means. But so I think we all worked on this when we were bachelor students. So that's typically a representation of a Koszul-Frobenius cone or domain. And this holds for like complex quaternion, octonion, except that the symmetric has to be replaced by self-adjoint. And that the octonion case, it's a very pathological case. So you have to restrict to 3 times 3 matrices. It's just because of the structure. And fifth is something that has nothing to do with the previous ones. And don't ask me why, it's just the way it is. The Lorentz cone, which appears often in relativity, which is given by this spherical kind of equation. And it has a very specific geometry of its own, which is of interest to, well, people in relativity and gravity. So these are the 5 Koszul-Frobenius cones. And I just wanted to add a little note for in case there are people who are fanatics of categories, that you can actually build a symmetric monoidal category. So it's not so hard. It's just like a symmetric monoidal category means that you can add your little Lego pieces together and it will still be a Lego piece again. So you can add cones, those cones together, and you still get a cone satisfying the initial axioms. So that's really very pretty. Right. And so I wanted to say that there are different properties occurring in the symmetric cones that you will see again if you want to work with information geometry, namely Amari's point of view or even Chentsov-Morozov's point of view. You'll find these recurrent structures appearing, except for 5 and 6, which are a result of, I don't know, Winberg and Koszul-Frobenius, which is independent and people from statistics didn't know about. Okay, so you have something called an affine structure So which means that you have a connection. So when you're doing parallel transporting a vector, you need a connection, the notion of connection. And you want it to be flat and without torsion. So that's what you call having an affine structure. You have an affine, flat, torsionless connection. So that's number one. Number two is the existence of a characteristic Koszul-Frobenius function. I think we talked about this morning. So this is appearing there very strongly, very useful, because it generates number three, Hessian metric, and generates number four, rank 3 symmetric tensor, so the Chentsov-Amari tensor, for example. And then there's more of an algebraic flavor. You have a Jordan algebra structure on the tangent space to the identity, and something called a pre-Lie algebra. So it's not exactly a Lie algebra, it's a pre-Lie algebra, also called Koszul-Frobenius algebra by some other people, like me. Okay, so that's the structure that you have. So just to make us feel comfortable, I want to recall what is an affine structure. So I mentioned that it implied, well, it's in a bijection. You need to have, it will imply, in fact, your connection, which is affine, torsionless, and flat. But this comes, if you prefer the definition from manifolds and atlases, it essentially means that your coordinate change here is an affine transformation. So we all know what's an affine transformation. You have a dilatation and translation, more or less. So that's what you have. It's going to be AX plus B, an affine transformation. So there exists an affine transformation and an affine structure on these Koszul-Frobenius cones. So that's an affine structure. Okay, and so characteristic function. So this is, well, I was wondering exactly how these people constructed the characteristic function, and I think it just comes from strong, brutal analysis properties which allow you to construct this characteristic function. So it's hard work, basically. But so we'll skip the hard work today, and we will just state the result that for any vector in your cone, the KV characteristic function is given by this. So you're integrating over a so-called dual cone. So you have a cone, and you can construct a dual one, and they're isomorphic. So you integrate on the isomorphic dual cone an exponential function of minus this evaluation. And so that's this characteristic function. So this this volume form is invariant under translations. And this is all invariant actually under translations. And when you get more acquainted to this cone, it's actually very logical because, well, you have this automorphism group given by a Lie group, which is just, well, everything is gonna be invariant. So that's how it works. So I was promising potential functions, and here we are. So a simple way, well, I don't know if it's simple, but a way to construct potential function is actually to take the log of what we just saw, this characteristic function. So this gives you potential function. And this actually is very convenient for Hessian geometers because you can actually construct in the right affine coordinates, in fact, a metric tensor that's given by this shape. So you're taking partial derivative in a given direction, partial derivative in another direction of this potential function phi. So that's a Hessian metric. So I can read it aloud. Given affine coordinates xi, and so that's why I was saying that if you're Hessian, you're automatically an affine manifold, right? If you have a Hessian structure, you have the affine structure because of this nabla, and nabla of this dxi is supposed to be vanishing. So these are your affine coordinates. And in these coordinates, you can define a metric tensor that looks like this. So it can be that you're working with a Hessian manifold and that you don't know that it is Hessian just because you didn't write it in the right coordinates. So that's Hessian structure. And so the hardest part was actually just to getting the characteristic function and the affine structure, and then you get everything like waterfall of results. So for example, this rank 3 symmetric tensor, if you suppose that your potential function is smooth, and so that's very important. So if you look in the historical articles, for example, by Calabi, 1954, he asks his potential function to be at least C5. But so if you want to avoid any kind of problem, you just say phi is smooth, and then you can define your rank n symmetric tensor. All the tensors will be symmetric, right? So for example, you'll have rank 3 symmetric tensor, which is very important, which is partial I, partial j, partial k of this potential function here. So plays huge role in Monge-Ampère domain and in the Frobenius manifold. No? So that's part of the axioms you need for a Frobenius manifold. Okay, so that's more or less the 4 foundations of the structure you're going to explore. Then whether you have Jordan algebras or another algebra, it's just going to depend on your situation. So for example, if you're considering those irreducible cones, well, then the tangent space as the origin will have an algebraic structure. And here in this situation, it is a Jordan algebra. So I did not recall the definition because I think it's already very well known since 1931. But so essentially you have Jordan algebras, and in the matrix representation of these, you can write it as matrices here of n times n symmetric real matrices or self-adjoint complex matrices. And here, this is the ugly duckling of the family. Here, it's a spin factor. So he is totally different from his siblings, 1, 2, 3, 4. He behaves independently, has his own life, his, I don't know, relativity life. So it's spin factor. Right. So this is our contemplation of Jordan algebras. So there is also his cousin for the symmetric cones. And so his cousin is not exactly a Jordan algebra, or although, well, there is a strong relation given by some isomorphism. So this is the Prilly algebra. So I just want to tell you that any associative algebra is Prilly, but the converse is not true. So if you have an associative algebra, you can think, oh, this is a Prilly algebra, actually. But yeah, so this difference is that you just don't have all the relations. There's like one important relation missing. So in particular, if you go to Winberg's paper 1963, he considers a multiplication operation, which is given by this. And as we can see, well, there's some Christoffel symbols, which are in fact constant structures of the algebra. And so those constant structures of the algebra are in fact defined by what we just said, rank 3 symmetric tensor, so this object here, and the metric, so your Hessian metric. And so this multiplication operation is going to be super important in the Frobenius manifold story because, well, roughly speaking, Frobenius manifolds are given by an associativity relation on the level of an algebra, which is on the tangent space to the manifold. So here, it's a commutative algebra, but it's not associative. That's why it earns this title of Prilly algebra, because we're lacking the associativity. Somehow, in some cases, you can obtain it and thus have a Frobenius manifold. So that's very important here. And so, yeah, just to summarize, I've been explaining the 6 main properties of these cones. And I was explaining how they are important in the construction. That's one point of view. So as I said, it's at the heart of many different theories. And this is mainly Hessian geometry theory aspect I was presenting. However, and this is going to be related more to the Souriau kind of approach, where we're leading straight to quotients of Lie groups, Lie algebras, and so-called symmetric spaces. So this is one approach which coincides and matches perfectly symmetric spaces. So roughly speaking, and I'm omitting a lot of details, a symmetric space looks like a quotient of Lie groups, G over K. So G is supposed to be a connected Lie group with a given involutive automorphism, whose fixed point set is essentially a compact subgroup K. That looks a bit scary, but it's going to be easy here. And there is a very nice classification by, I think, Japanese school, namely Nomizu, who classified symmetric spaces into 3 main classes: compact, non-compact, or just Euclidean. So Euclidean, well, we can all imagine that the curvature is going to be vanishing, right? It's like this 3 space, for example, it's Euclidean. And the curvature is vanishing. But then you have these 2 other classes, compact and non-compact. And in the compact case, you have non-negative sectional curvature. In the non-compact case, it's the opposite, non-positive sectional curvature. So, little challenge test for you. Tell me, in which of those 3 classes do the Koszul-Weinberg cones belong? So one hint is certainly not Euclidean, right? Because it's kind of cone. Well, it could be Euclidean. So no one wants to. Yeah. So wait, okay, I'll let you know after. Okay, so we have this automorphism group, as I was mentioning. So let P be our strictly convex cone. I drew it on gray on the right-hand side. And we have an automorphism group, which allows us to, well, we have transitivity. Y is equal to gx for given G. So G here will be the group of all automorphisms, and I'll define K if P be this stability subgroup at a given point E. And TP also plays an important role. It's a maximal connected triangular subgroup of G. Then, well, this is, I don't know who did this. It was maybe Carton, something like that. So G is given by K times T, where K and T just intersect at a given point, and T needs to act simply transitively. So that's an important property, namely if you consider the Lie algebra aspect, because it leads to this decomposition. And in particular, we have these relations. Okay, so this is the answer to the challenging question. So we have this table here where, well, actually it's SLNR or GLNR. It depends if you want the determinant to be 1 or not. So GLN or SLN, SLNC, SLMH. So this is the ugly duckling. So he's a bit special. And octonions are also kind of special. So we have these here for the compact structures. So J is the dimension of the Jordan algebra. And that's the dimension of it's supposed to be n here. Okay. So this was just recollections that I picked from Frederick's slides. But this okay, we know it. So result, I can show that they are non-compact symmetric domains, and the sectional curvature is 0 on an algebraic torus. So this is good news because it means it's going to be Frobenius somewhere and it's going to be on a torus. And in fact, tori are Frobenius manifolds. And if you're in the complex case, the simplest kind of Calabi-Yau manifold also. Otherwise, if you're not on this algebraic torus, sectional curvature is strictly negative, and well, you can call it Cartan-Adamar space. Okay, so I'm gonna go a bit faster now because I see that I'm speaking way too much. So I wanted to recall a bit about Souriau's model with applications in particular to KV cone. So as we saw this morning, we have a geometric temperature, and an element which is a geometric temperature will lie in a Lie algebra G of a given group. So M is a symplectic manifold. I have a group action G on it, Lie group. And so obviously it has a Lie algebra analog and is dual Lie algebra analog. So G and G star. So here we will suppose that this will contain a geometric version of temperature, while the G dual will be, in fact, the geometric heat. So that's the Souriau model. And we will define momentum, so that's very important in particular when we go back to the Koszul-Weinberg cone, this momentum business from M to G dual. Right. So that's essentially, well, a very rough summary of the main objects we need. And so here I can recall some relations. In particular, well, we can say hello to a Hessian metric. So that's what we just met on the first part of the talk. So we had in different coordinates, of course, but this is exactly corresponding to the Hessian metric on the cone. And our say hello again to KV function. So this is our potential function, and we can all recognize this formula we just met a few minutes ago. So where U is going to be this momentum map, and beta is going to belong to your Lie algebra. Okay, so this is giving you the Souriau entropy, and we can play with the formulas and obtain like complementary relations. For example, the heat is this partial derivative given by this KV function, and reciprocally the temperature, or it's 1 over the temperature actually, is partial of this entropy with respect to Q and lies in G. Furthermore, there exists a Legendre transformation between this object Q and beta. So that explains you exactly how you can pass from one to the other via entropy or via KV function. Right. And finally, this last relation. So that's really important in the model. Of course, we have this adjoint representation of Lie groups, which occurs. So if G is your Lie group, then you can define psi, the map from the Lie group to the automorphism of G, as follows. So given an element in the Lie group, you can obtain this conjugation object, GH G inverse. And your adjoint will be living on the level of the Lie algebra. So GX, G inverse, where X lives in the Lie algebra. Right, and these are following relations. So that's important, in fact. So here I was sticking to the notation that we saw this morning. In particular, we denote things like that. And I think this is very important here. So given an element in G dual, a coadjoint orbit is going to be given by the following formula. And the remark here is actually quite powerful because these coadjoint orbits carry a symplectic structure, which leads us to this very important statement: a symplectic manifold, which is homogeneous under the action of a Lie group, is isomorphic modulo some covering to a coadjoint orbit, possibly affine. So that's really powerful because when you go back to the KV cone, that means you can actually consider it from a different point of view, which will be this coadjoint orbit. And this is quite interesting, actually. So we can recall the fundamental equation of Souriau. So the one you see on the bottom of the slide. So that's what he really shows that. So it's a commutative diagram. So as a mathematician, I would say, why should I do this picture when, well, you can just do a square diagram? But actually, it's very interesting that you have these arrows here. And, well, you can go from here to here via this theta map here. So yeah, so you can go all the way from here to here. Sorry, I'm not really very good at this. And via the other way here, which is summarized in the formula. So Q star is a joint star of Q plus this object, extra object theta, which lives here. Right, so that's the fundamental equation. So what time is it? Yeah. Okay, so I would have wanted to spend more time on this, but there's no time to lose here. So I'm going to go now towards Gibbs density. And so, well, very intriguingly, we can say hello again to our KV cone. Why? Because, well, we're taking this exponential of this evaluation, and we're just simply normalizing everything here in order to get a Gibbs density. So it's a kind of normalization, and we're in the world of probability or Gibbs density. So in particular, I recall that U is a map from M to G dual, and that Q is given by this. So it's a partial differential of phi with respect to the direction beta, so it's temperature, and phi is minus log of, well, it's our KV potential. So KV potential in this KV cone is really everywhere in this business here. This leads us finally to express a property of invariance. So the entropy being this map from G dual into R, sorry for the comma. So you're to every element Q, you obtain S of Q. You have this invariance property. So S of Q of the joint, well, it's just S of Q, right? Like shortcut. And in particular, this relation that we've seen, I think just previously, yeah, theta is a notion of a cocycle. So it's a Souriau cocycle here. So that's mainly the situation of this model. So I'm really summarizing it in a few words, but that's what's happening. So more properties of entropy. So this morning we showed this actually. And okay, I'm skipping directly here. So what I wanted to say, oh yes, I wanted to use my previous diagram, commutative diagram, and say that you're parametrizing in some sense by this Gibbs canonical space. And in particular, as we highlighted this morning, well, yeah, entropy here will be invariant
whereas the other objects here on the level of characteristic functions are not going to be exactly invariant. So that was explaining what's going on here. So this is the little surprise of the end. So I wanted to add, so that was not in my abstract because it's recent result, but I would like to put all this in the context of the theory of Landau-Ginzburg. So initially, a theory of Landau-Ginzburg is a theory for superconductivity. And in particular, you have, for example, well, this is the physics explanation. You have this metal, very thin metal and electrons in there. And you have Cooper pairs. So it's pairs of electrons with spin up and spin down. So they pair up like this. And you have the space of probabilities of finding Cooper pairs, which lives on this light gray box. So this is a very rough definition of Landau-Ginzburg theory. But I want to say that all the situation I've been talking about previously will fit in the Landau-Ginzburg theory a la Koopman von Neumann. So as we said previously, we had this space of these Cooper pairs with these electrons. Let's forget about electrons, we're mathematicians. And so we're going to work with a symplectic manifold. So you have this symplectic manifold, which represents a phase space. And above, well, you have probabilities of having Cooper pairs. So in particular, probabilities are, well, density of probabilities given by something like that. So that's your density of probability. So how does it appear now related to Landau-Ginzburg? Well, psi is interpreted for us as a kind of wave function. That means a L2 integral function with complex values. So this lives in a Hilbert space of L2 functions. And so the great news of, well, what I can show is that this is actually torus vibration, because we're going to have this equivalence class. And as we saw in the previous talk, we had this norm of Z1 equals to norm of Z2, giving a torus. And this is exactly what's going to happen here, that we have equivalence classes of functions, and thus forming the norm are all equal. So it forms actually a torus fiber. Furthermore, there is nice relation to Galilei group in the Souriau's approach. And so I would like to add that this is exactly what happens here too. We have an Euclidean group, which is a subgroup of Galilei group, which will be acting on this Hilbert space. So that's Euclidean Lie group, semi-direct product of groups of rotations and translations, but preserving the norm. And you have Euclidean Lie algebra. It's logical, right? We're preserving the norm, so you can do anything you want as long as you preserve the norm. So Euclidean Lie group is exactly what fits the best. And it's Euclidean Lie algebra cousin, so it satisfies this. So that's the Planck constant. You can put any constant you want, any symbol you want. And so the proposition is that this vector space of self-adjoint linear operators acting on your Hilbert space forms an Euclidean Lie algebra. So, oops. So, yeah, you'll have Euclidean Lie algebra acting somewhere on this. So unless I'm almost finished, well, when you talk about Landau-Ginzburg theory, it's a bit silly not to mention the Landau-Ginzburg equation, which is kind of central in it. So let me just express it. So the Landau-Ginzburg free energy is given by this very long formula. So these are positive constants, A, B, M, ampere. And so F0 is like a free energy density of something called a normal state. And then you have other things which represent increase in energy or increase in superconductivity. And that's just a Landau form. In other words, you can derive from all this free energy business a Landau-Ginzburg equation, which looks like this. And actually, the nice news that I show is that stationary solutions to the Landau-Ginzburg equation are invariant under the symmetry group of Galilei. So that's just slowly. So we went from the cones to thermodynamics, and then from there we went to superconductivity via this Landau-Ginzburg, and now we're back to Souriau's story with this Galilei. So to summarize the space of density probabilities that we just met below here, D is a Monge-Ampère domain. It's a Monge-Ampère domain, elliptic Monge-Ampère. So we can prove it using Monge-Ampère for probabilities. The KV cone is a Monge-Ampère domain. And well, how many slides did I do? Yeah, okay, last theorem. Okay, I'll skip this last theorem because it's beautiful. So we know or not that Landau-Ginzburg, well, Kontsevich said that Landau-Ginzburg models are a good formalism for considering homological mirror symmetry. And so what do I do is here that using this model I explained, and which is in fact related to the Souriau story, there exists a Monge-Ampère domain parametrizing a pair of mirror dual Calabi-Yau manifolds. And this Monge-Ampère domain is the one we just talked about, space of density of probabilities with torus fibrations. You can take your favorite real Koszul-Weinberg cone to try this because it parametrizes a complex torus, which is the simplest Calabi-Yau math. Many thanks.
Okay. Question by Rita.
So thanks for the excellent talk.
Thank you.
As you said, I'm curious about the last result that you were stating. So sorry for being a bit provocatory with my question, but because so I'm like, okay, Monge-Ampère domain are kind of ubiquitous, right? They come up this symmetric type of domain. So it's not surprising that they parameterize pair or mirror dual. I mean, what I'm trying to say is that are you using really something of information geometry, something of the theory to prove the result, or is just a coincidence that in the end you see my question, right?
Yeah,
I don't want to be mean, but it's
no.
Okay.
No, yeah, that's a great question, actually. Well, so I didn't say much about it, but so as I said, I'm starting with Koszul-Weinberg cone. Okay, so this is just the space of matrices. I can show it's pre-Frobenius and it's Monge-Ampère domain. Okay, that's one thing, the story. Then I read about this Souriau model. And then I was like, okay, this behaves a lot like this KV cone, right? There's a lot of things going on. This, as we saw, this metric I of beta appearing, this Hessian metric. Sorry, maybe faster. Okay, this Hessian metric, we had this KV function, so we're really in this KV cone kind of situation. Okay, and then I was working, so there was another conjecture by Kontsevich-Seibelman, which was saying, okay, in a given limit, there exists pairs of Calabi-Yau manifolds, which are, well, mirror pairs, parametrized by a Monge-Ampère domain. That was a conjecture. And so it's like, so there were different papers, but they were never mentioning it was Monge-Ampère. And then there was this first suggestion, you should look at Landau-Ginzburg models. So that's what I did. So from the point of view of Koopman von Neumann, which is not what people in algebraic geometry do. So it's like a completely different point of view without being too different. And via this, you can have, so you have this Hilbert space parametrized by this density of probabilities. So here you have information geometry, density of probability. Okay, so that's actually Monge-Ampère. So it fits Kontsevich's prediction. So that's exciting. But on the other side, yeah, it's maybe really interesting to say more about this probability and density parametrizing those Calabi-Yau manifolds. So the construction of mirror pairs was actually, I took something standard, which was done by, I think, Hübsch, Kravitz, and I'm sorry to forget his name, but someone else. So that was standard, but what was not standard with this Hilbert Hilbert space thing, which turns out to be actually torus vibration, which I wouldn't have expected. It's a weighted projective space. Well, generates weighted projective space. So very exciting maybe for tropical geometry people. And so, yeah, so what I'm doing is I'm showing that all those three different topics fit into one. That's what I'm doing. Yeah. Yeah.
Okay. Last question.
Thank you for the nice talk. I would like, in the work of Saito, there is a way to construct cones by quotient space by reflection groups. And also has to do with the Weinberg work. And you have cones. I would like to know if you have some underlying discrete group behind those cones.
The KV cones, you mean here?
Yes, yes.
So I think the question you want to ask is rather, given the LG models constructed by, so there was a result by Kyodo 1 and this Kravitz, Hübsch, and the first one I keep forgetting. So they construct, as you said, this orbifold. So you have a hyperplane and the weighted projective space quotiented by an automorphism group, G, for example. And its dual is constructed in a very nice way, just using transposition of matrices. So it's incredibly, well, simple in some sense. And so what you want to say, I think, is that you have these two objects, which are mirror duals on the upper part of this picture. And they're parametrized by, for example, a KV cone. So for example, the Koszul-Weinberg cone could be parametrizing a pair of Calabi-Yau. How do we know this? Well, if you go back to the very first slide, I don't know if I can do this. Well, it's going to take too much time.
Yes.
Yeah, okay. So you had this upper half plane parametrizing tori, moduli space of tori in number theory. And so the KV cone, well, it lives in this Siegel upper half plane. So you're actually, and the torus is Calabi-Yau manifold. So you can actually do a baby model, toy model of this mirror symmetry story. But the cone lives, as I said, as the base space in the base space here on the level of Cooper. No, I'm sorry, on the level of probabilities here. So D will be, for example, in an example, a KV cone. And Calabi-Yau will be living up there here.
Okay.
Voilà.
I just have one remark of vocabulary. Koszul used the term cone convex saillant.
D'accord.
Classically, the translation is sharp convex cone.
Yeah, I saw the slides.
Yeah.
I didn't know. I don't know. So, sharp is better, actually.
Okay.
Yeah, sharp.
Okay, thank you. So we have a 15-minute break, and we will continue with Professor Faso just after the break.